To bring things back to something that is a concern for programmers, let's talk about remanence. Suppose you have this program that decrypts and does it in a good way somehow. It's going to load a private key from a file, say, then it's going to do an RSA decrypt. Maybe that's been hardened some way so that it doesn't leak information about the bits. And our main function is going to call that decrypt function and then call work. As we have been doing recently, let's consider what happens at the next layer of abstraction down in the machine code layer and the C stack layer. When we call decrypt, then it's going to make room on the stack for the local variable that is private key. And that key, which I'll represent by a password super secret here, is going to be sitting on the stack. Then the RSA decrypt function does its work, and then decrypt returns, and that variable is no longer valid on the stack. But the return instruction from decrypt doesn't actually erase anything on the stack, it just moves the stack pointer up. When we get inside the work function then, that work function also makes space for its local variables. It will make space for the buffer local variable, but nothing about making that space actually zeroes out the space. It just drops the stack pointer back down. So until it is initialized, buffer actually contains the super secret that decrypt was using. We can't actually read it off legally in C because it would be undefined behavior to read this buffer that we have not initialized, but sometimes go wrong and C programs do read a buffer before it is written to. And there's a danger that super secret is still sitting in that buffer and that the read of that buffer is in some place that exposes what was inside of it. So as programmers, we have to be aware that stack allocated values are not erased on return from the enclosing function. You should also be aware that heap allocated values are not erased by free. So if you malloc some memory, put super secret into that memory, and then free that memory, probably the word super secret is still sitting out in memory, and it'll still be there when another malloc gives back the same memory. One thing you might try to do in either of these cases is erase the variable before you return to make sure it's not there. But now we're back in the world where a C compiler might not do what you intend for it to do because what you write doesn't matter at the level of the C program. For example, here I've got a work function. It creates a buffer and it does something with the buffer. And because I wanted to zero out anything that might be in that buffer, I've written a memset call here, which takes a buffer, the byte that I want to put in the buffer, and the length of the buffer. So my intent here was to write all zeros into that buffer before returning. But if you take this little program and run it through your C compiler with normal optimization options, you will find that the generated machine code looks like this. There will not be a call to memset here. After calling go, we set the return value to 0, and then just pop the stack without zeroing any memory. And the reason for this is the C compiler can tell that no one should be able to look at the 0 bytes of the buffer after we return, so there's no reason to actually put those zeros there. The best you can do in this situation, if you really wanted to do this, is try to write enough code to confuse the C compiler that it is forced to zero out the bytes. A better option, when the language provides it, is to use something that specified the language as having the meaning of actually zeroing out the memory. In Java, for example, there's a secret key class and there's a key class, and these classes behave the same way, but the destructor for the secret key class always zeroes out memory. Then there's less possibility that the old bytes could get viewed by someone. And secret key works because the Java compiler cooperates with the implementation of the secret key class to make sure that the zeroing actually takes effect. One thing you don't have to worry about is at the operating system level, when you call mmap, you will always get well-defined content in the allocated pages. The operating system will not take a page that is previously used by some other process and give a different process that calls mmap the same physical memory without clearing what's in that memory. Otherwise, it would leak between not just two different functions, but two different programs running on the same operating system. So mmap will always zero out memory that it gives as a fresh page to a new process to avoid those kind of leaks.